being broadcast to YouTube Live, which means that this video will be available to you. You can watch it right now and you can have the video immediately afterwards. At the same time, let me go and start the recording. All right, guys. So in this workshop, okay. So in this workshop, we have two projects that I asked you to do. One was prescriptive. I said, go and analyze the archive data set. This data set is of researchers who have submitted their works, preprints of their work, pre-publication versions of their work to the archive site. Archive is perhaps the largest network or site of preprints. Whenever people come up with some discoveries, at least in the fields that I have belonged to, which are theoretical physics and computer science, you don't go to a journal and ask them to publish. Your first reaction is you summarize your research and you submit a preprint to archive. Once you submit it, it already becomes available to all the researchers in your community, and they can discuss, they can think about it. And usually by the time something gets peer reviewed and published, many, many months have gone by. These days, especially in fast moving fields like artificial intelligence, data science areas, uh, you don't want to wait till something gets published, which may take up to a year or more. You want to know about the breakthroughs as they happen. So it has become very common for us to every day treat archive as some sort of a news site. One of the things I'd recommended to all of you, if you remember, was this website called Archive Sanity. You can go there and some people curate the best articles or what they thought are the best articles, best publications or research work. And they sort of annotate it with comments and this and that or something or the other. And they make it available. There are a couple of YouTube channels which do the same thing. They'll take the breakthrough papers or some important papers being talked about and they'll discuss it in detail. So we'll focus on archive. This particular data set is there on Kaggle. Somebody has collected it. It's basically only the metadata of articles published there on the preprint site and is limited to the domain of data science. So it is AI, there's that machine learning and so on and so forth, these areas. So it is not all of the areas that archive covers. Archive is vast, but it limits itself to machine learning because we know this field. So when you do the analysis, you will have some intuition. So for example, if you find that if you're looking for the most published author and a name pops up, you can decide whether this analysis looks right or not, because you probably know who the most published authors are, right? Who are the most referenced authors or cited authors and so forth. So that is why I gave you the archive metadata dataset. It is also something that is fairly manageable in the cloud and on your powerful laptop, if you have one. Actually, even on ordinary laptops, though I highly encourage you to do this in the cloud, not on your, if you don't have a very powerful machine, don't do it at home. Do it in the cloud. In this sort of analysis, and more in the modern world, when we analyze data, there are three different axes, even for just exploratory analysis. The first is looking at tabular aspect of the data, a data frame. You have data as a data frame, then you can do your basic bar charts and count plots and pair plots and all the things that we have been doing. Then a data like archives data, there's a networking aspect to it. Researchers collaborate, they network. Research papers refer to, or preprints refer to each other. They cite each other. So you can you can observe the collaboration network between these researchers. You can also create a network of citations from paper to paper, or a bipartite graph of, researchers citing certain other researchers, that is a citation network of researchers, citation network of papers, or a bipartite graph in which authors cite some other papers and so forth. You can do all this very straightforward way. These days, networking libraries have become pretty powerful. We will use a library that is quite popular in Python. It is called NetworkX. For R, we'll use a library called iGraph. iGraph is or implemented fully in C. It's much faster, obviously. There is an effort to port iGraph to Python, but I don't think it is as popular as NetworkX. NetworkX is written entirely in Python. For that reason, it's a bit slow, but the syntax is very Pythonic, very natural to Python, which explains its popularity. We'll use these two to begin with. Then we can do text analysis. After all, these articles, these research papers are about some subject matter. They contain abstracts. If needed, we can programmatically go and get the content of those. We can get a PDF versions of those papers. And from the PDF, we can extract text. There are all these programmatic means to do that. Apache, for example, gives you lots of open source tools to do all this manipulation. For text manipulation or text processing, you should use the NLTK library to begin with. It's pretty popular. Let's start with this. Later on, you can use the GenSim and other things to do semantic analysis. And we can use that as a starting point. Later on, I mean, as you grow this project and go into the deep learning, you can carry forward this project because you can apply your transformers and other things that you will learn in deep learning on the same data set. So this starter project that I gave you deliberately was designed in such a way that you could carry forward to the next workshop. So to summarize, we'll do the archive data set today. I'll give you only the starter code. I won't do much. The idea is that you should do and learn. At subsequent time periods, I may release a larger and larger part of an analysis, but it would be far better if you took it in your own creative direction. But the three axes on which you must address this analysis is first, as a data frame, as a tabular data, the tabular data analysis. The second thing you must do is a natural language processing. Use basic stuff at this moment, since you are not experts in NLP. Use the natural language toolkit. Do basic things, see if you can create a word cloud of the most popular authors, word frequencies. And some of these things I will do right now. You do that. And the third is networks are becoming increasingly a central topic, and one of the central topics in contemporary data science. Everywhere we have networks, our friendships are networks, we have professional networks, researchers write paper, they have collaboration networks, and you have citation networks and so forth. So you must also learn network analysis. Now, those of you who took ML100 would remember that we went through a couple of sessions of network analysis before. So have network analysis also as a dimension of your analysis or of this project. So with those words, let me start sharing my screen now. And let's go with this. So here we go. This is a notebook, which I hope all of you can see. I'll increase the font a little bit. Let me know if I need to increase the font even more. Is this fairly legible to all of you?
Yes.
It is legible. So by now you must be familiar with the Jupyter notebook and the way we write it. This is your standard table of contents. As you can see, it's a very short table of contents, unlike the other notebooks that I've released. The point being that this is just a starter code. This is your basic preamble, themes and other things. And this just ensures that all the libraries that we will need are installed. Actually, we won't use Torch. Deep learning is for the next workshop, but as a motivation, if you can, it would be even better. So we're going to do exploratory data analysis on the archive data set. By the way, go beyond exploratory. If you can build predictive models and so forth, great. That's what I hope you do. But let's start with exploration of the data. So the basic imports are, by now, these are all the usual suspects, and you should be quite familiar with them. NumPy, what does NumPy do? It gives you support for high performance arrays and matrices and operations on them. Pandas provides you a support for the data frame construct and its manipulation. Pandas profiling is an automated tool to give you a preliminary exploratory data analysis, right? Like now, when it comes to handling networks and the investigations, NetworkX is a very popular library. Again, as I mentioned, it is in Python is very popular. And for those of you who are doing it in R, use iGraph. It is a bit slow. iGraph is lightning fast, fairly, but the NetworkX can be a bit slow for large graphs. And you will see that when you actually run it. So once you are done, once you reach the limits of NetworkX, then graduate to a bit more powerful library, for example, NetworkKit and so forth. There's a very close parallel between NetworkX and NetworkKit, and you can make things much faster, better. Because today is the first time we are doing the lab in networks, I will make the code dead simple. I will not focus on making it prettier or more beautiful. So just as a recap, some of you may remember that we did in ML100, I had looked at the Facebook graph in one of the sessions. I'd said that look at the friendship networks for a small group of people in Facebook. And when we did that, we created the graph. Those of you would remember some of this analysis. And we created this beautiful visualization of the network. Right? When you look at these real world networks, you realize that they have structure. Do you notice how people or their relationships are clubbed together, friendships are clubbed together into communities, right? And this is sort of an ego network of a person. And when you look at this friendship, so your friends themselves form groups of friendships. And you know that you have a professional, some friends are from your professional life, some friends are from your social life, some friends are probably from your tennis playing club or your photography club. Then within this, you can also look at the degree distribution, like how connected is each person to other people in the network. So these are called degree distributions. Uh, it's one of the things that you should do if you can in this. It's really helpful to do degree distributions. And then to detect the communities, when you look at that, there are all of these communities. Can you detect the presence of communities? It's very analogous to clustering in Cartesian data in Cartesian space. Right? When you have data in Cartesian space, it's a real valid space. You do look for clusters, k-means clusters, density clusters, and so forth. In the world of graphs, the more appropriate term is communities, because you don't have a notion of a very obvious notion of distance. You can create a notion of distance, but it's not a Cartesian space. You still can create notion of distance, as in how many hops does it take to go from one person to another, and so forth. But it's not a Cartesian space. So what you look for are communities. These are the communities that you find. And sort of we went through that. I will leave that aside. Today, we are not expecting that level of sophistication. If you can get there, as you can imagine, these are all like 4 or 5 lines of code. But since you're getting started, some of you with networking code, I will skip that. You can now move forward. So that would be the networking library. There's another library called PyTorch Geometric. For now, skip it because we'll need it in the next workshop when we do deep neural networks. Right? For plotting, of course, we use Matplotlib and Seaborn, no brainer. By now, you should be familiar with. For machine learning, we'll use scikit-learn. Once again, it's a ubiquitous Python library for machine learning, and we are all familiar with it. PyTorch, a high-performance GPU-based or GPU-optimized library for deep learning. And finally, we'll use Folium for visualization of geospatial data. Now, where you will use it, I will leave it quiet. You can figure it out how you would represent, how you can do any geospatial representation of the archive data. How do we load the data? So where is this data from? I've given you guys the link to it. So somebody has put just the metadata of it. There are multiple versions. There are a couple of versions, 5 gigs and 9 gigs of data, which are complete data across many, many communities in archive. Those are huge data sets. It's much better to play with data sets that you can handle in your notebooks when you're just starting out. You don't want to run a computation that goes on for like 2 days. So the smaller subset of data is better. It's about 24,000 authors or so. Or entries, so forth. So let's look at this data. When you look at this data, oh yeah, 41,000 entries. So how do you load data? This comes in JSON format. Pandas, of course, can load it just fine. So when you do it, change this line. Change it to wherever you have downloaded the JSON file for this data. This should look familiar. What are we doing? We are describing this data. So when we describe the data, we notice that there are all of these fields. These fields are described, by the way, if you go here and you click on this, you will notice it described. So these are all taken from sorry, this data is based on about this file. Okay, now we need to get to the data. Yeah, this is the data and its descriptions are given somewhere. Where are the descriptions given? No, the descriptions seem not to be given. But if you look at this, this is actually a subset of other archive data. And other people have given more of a, let's say we go to this 2 gig distribution, yes. So when you look here, what you have is a subset of this. So what I will do is I will just copy this, or maybe not. I will make a link to this for the documentation. Archive, University Archive. Let me add it to this to understand this data is taken from Cato. How to understand the fields. So if you go here, you can see the descriptions there. So what are the things? ID is a unique identifier. Submitter, who submitted the paper, not of terrible importance. Typically, a paper has multiple authors. One of the questions is, in general, how many authors does it take to write a paper on the average? And we're going to find that out. Title, comments, number of pages and figures, journal ref, information about the journal this paper was published in. That is, if the paper finally gets published, you put journal refs. This is a unique thing. Nowadays, people are making an effort to give a unique document identifier to all CS documents, public documents. So in that spirit, there is a DOI. Abstract is essentially a summary of the paper. It gives you what the paper is about, typically at the top of a paper, even before the introduction and right below the title, etc. You put the abstract. Categories speaks about which are the keywords or categories to which it belongs, which is self-descriptive. Versions, sometimes papers can have different versions associated with them. People keep resubmitting it after fixing typos or corrections to their calculations or graphs and so forth. So that is that. One good thing is that any one of these paper you feel like accessing, you can always directly go access it. Right? It's a very publicly available data set. A typical data looks like this, as you can imagine. Right? Entry in the data looks like this. So we'll go and explore it ourselves. We take this data, we load it into an archive. When you look at it as a data frame, you notice that these are the columns. So by now, they look familiar. There is only one catch. If you look at the first few rows, you begin to realize that, see, this paper has Gordon and somebody else. So author is actually a string containing many authors, all the authors of a paper. So the title author is a bit of a misnomer. The rest of it is standard. ID is link month. Month means from 1 to 12. Year of publication, title of the paper, tags. So once again, you have these tag terms. You should give it the same treatment. So this is a point I was making. If you look at the first row of the data, some row, and you look at the author, it turns out that the first author, because it starts with A, is somebody named Mr. Osman and Mr. Washinch something. Well, we need to break it up into two different authors. How would we do that into the number of authors? And this is a little bit of regular expressions. Do you guys know string matching, regular expressions? When you get a complicated string and you want to extract only what you want, there is a very powerful technology.
Regex?
Regex, yes.
Okay.
Regex. That's what it is, regular expressions. It's a technology that helps you extract what you want in a very, very powerful way from the text. And so if you look at this, let me give you an idea of what it is. Look at the names. What we want to extract is this and this, isn't it? But you get this long, complicated string. How can you do that? You notice that semicolon, space, and single quote. This is a unique identifier that helps you find names, isn't it? And it ends with a single quote. So that's what I did. I'm saying start with a semicolon, a space, and a quote. And after that, as many characters as they are present, till you hit the first end of single quote. When will you hit the first end of single quote? Here. So if you look at this text, you would get this kind of match twice on the two authors. So you compile the string, you compile the pattern that you're searching for, and now you can give it any string and it will return you the authors. You'll return you the string match. Now, when it returns, we don't want the first, second, third character. You want to start from the fourth character, and you don't want the last character either. That is why you take the substring 3 to -2. So there's a lot happening here. Play around with it, and you'll realize.
List.
Go ahead, please.
No, sorry, nothing.
Yeah. So when you go around, you'll realize that a lot is achieved in a single line here. Right? We have managed to find all the authors as a list from text. And this is the power of regex or regular expressions. They help you do a lot in just a couple of lines. Right? You notice that a function that is just one line has achieved a lot. Now, you may also notice that I tend to give hints. Do you notice that there are hints here? One of the things I didn't optimize is to say that whether str is null. What happens if this is null? Actually, this will take it fairly gracefully and return you nothing, I think. But you can try what happens with null. Maybe it will buff, who knows? I didn't check that, I should have. So, all right, so you get this. Now what do? I have a function and I can apply it to every, in the archive data set. You see that this data frame I called archive, isn't it? In this archives author column, I transform every value of the author column by this function to authors. So what will happen is the author column will now be replaced by a list of authors, isn't it? And we can see that. If you notice, we now have authors. And then once we have that, we don't need the author column anymore. We can just delete it, drop it, and then we have this. Let's look at a few rows of data. When you look at this rows of data, do you notice that it comes out very well? All the authors are coming out very well, much better, isn't it? As a list of people. Right. Now, let us do some very basic analysis on this data. Let us look at, for example, how many submissions were made in a given year. That is easy. You know, some of these fields are numerical. For example, a month is numerical, isn't it? A year is numerical. So you can do sort of group bys and counts on that. So you're doing a count on the number of submissions every year. So as you notice, research has been rising up exponentially. It's sort of one of the first things that surprise people. People think that research grows linearly, but actually more research has been done in the last 2 years done in, I think that statement is true, more research has been done in the last 2, 3 years than in the entire history of mankind. Right? So the pace of research is accelerating, completely accelerating. And you can see that effect. So for example, well, archive is not a really reliable measure of how much research is done, but as a very rough and ready thing, you can see if you take, well, 2018 is not complete here, so we should ignore it actually. This and this, if you put together these two, you realize that they will add up to a number. Let's see, if, do they add up to a number or not? This is 12,000 plus 6,000, 18,000, more than 18,000. If you add up all of these, let's see what it comes to. Little more than 4,000, 3,000 approximately, 4, 7, and another maybe 3,000 or 10,000, maybe a little more than 10. Let's all round it off to 11,000. 11,000 and a little more than 2,500, 13,500. You get the idea, isn't it? Maybe there's to a couple of 14, 15,000 and so forth. So you realize that if you add up the last 2 years, you'll end up with the same number as up till then. And it just shows you how fast, at least this field of artificial intelligence and machine learning is growing. More work is done in the last 2 years than seems to have been done in all of the history of the subject. That is a remarkable insight, isn't it? And this is the point, when it is one thing to pick up the technology, but gradually you should start thinking, what is this plot trying to tell me? We may say, do people submit more research papers or finish more research in any particular month of the year? When you try to plot it, you get a plot like this. So my observation was that there's nothing very remarkable about it. Uh, these small changes, I wouldn't read too much into it. Next year, it may be different. Going forward, it may be different or something. These are fairly small variations from 2,700 to about 4,000 something, 200 or something. So not much, a little bit. March and November seem to stand out a little bit, right? But not much. When you look at researchers, one of the basic, so now you can start posing your questions, experiment. In a field, one of the first questions you ask is, who is the most published author? Number one, who is the most prestigious author, right? That everybody is citing or referring to. Who is the person people have done, who is the one author who has the maximum number of collaborators? In other words, has collaborated with a whole lot of other people, right? You can actually start answering those questions. All we do is little bits of code. You take all the authors. First from that archive, you extract all of the authors. Do you notice that from the authors column, what am I doing? I'm adding all the authors to an existing list. And from there, I'm saying we found these many authors. Once you find those authors, you notice that there'll be duplicates. The same author has published 2 papers. He'll show up in the list twice. Folks, I hope this is obvious to you, isn't it? If I just go and take the authors for each of the papers and add it to a master list of authors, suppose you have published 3 papers, your name will show up thrice in this list, isn't it? It shows up when we do a distinct, you see that there are 132, 679 published authors, but because they are duplicates, the unique number of authors is 60,000 approximately. So guys, think about it. There are 60,000 people who have done some form of non-trivial research in this field and contributed to archive. Right? This contains great luminaries, as you will see, and it contains, well, everybody else like you and me. Hope this is an encouragement for you to also do a good project and write your own archive, preprint and submit it. Discover something new and submit it. It doesn't have to be great. It just has to be original work of relevance to the field and of value to the field, right? So the only 2 things needed to publish. A, it must be original, and it must have some use, right? So for example, you cannot go to an obscure library and count how many books of poetry are there and how many books of this and that or whatever. If you do that, you may be the first person who has counted that. So you have produced something original. But perhaps that data that you produced or the article that you wrote may not be of much value at all, right? So that is something to know. Moving forward, we can ask who are the most published authors. right? So we get these authors. Who are the most published authors? How would you do that? That is very easy. You can just do a box plot. Once you create, by the way, this library is very useful. I often see people use dictionaries to create, word frequencies and so forth. Here, the word being the author. You can do that, of course, by all means, but it is more elegant to just use this package. This library in Python does the job and all in one line. And so then from that, you can ask for example, I happen to pick a 50 most popular or most published authors. And I created a data frame for it, and then I visualized it. When you do that, do you notice that who's the most published author? Joshua Benji. Anybody knows who that is? Has heard of Joshua Benji?
No.
Okay, he's the author of your textbook for the next workshop, and he's a luminary, huge luminary, big guy. I think after Geoffrey Hinton, the next name you hear is his. But do you notice something quite remarkable? Geoffrey Hinton is nowhere there in the first, at least I didn't find him in the top 50 published authors, right? So it just alludes to the fact that just because you write a lot of papers doesn't make you great. Sometimes great authors, they write sparingly, but great researchers, they write sparingly. But when they write, it's immediately considered a breakthrough. They come out with something very, very non-trivial and advance the field. Right? So, but Joshua is a very prolific writer, and he's also a very, very high quality researcher. So obviously, you see him here. These names, as you do deep learning, they will gradually become familiar to you. Quite a few of these names will become familiar to you. Right? The next thing that you may ask is, authors collaborate. So now you may collaborate with 10 different people, they may collaborate with other people and so forth. So you can imagine that there is a network of collaborators, isn't it? So for example, you may ask this question, between me and that other researchers, how many links of collaborators do I need? So I may have written a paper with somebody who may have written a paper with somebody else, who may have written a paper with the person, the target person that I'm thinking about, right? So then you would like to, for example, pass a message through and try to do a direct collaboration with these intermediaries as your reference and so forth. So it is quite common to look at collaboration networks. I should say collaboration networks rather. Collaboration networks. Right? So guys, you notice that I'm posing the questions, things from common sense that seems relevant and doing it. So this code, I've tried to keep this code as simple as possible. All it does is from the author list, if two authors exist in the same paper together, I add them to a set of pairs, tuples, A comma B, if A and B happen to be in a paper at the same time. So suppose A, B, C are in the paper, how many pairs can I extract? I can get A, B, B, C, and A, C, 3 pairs, right? So we do that. So this is what I do. For every author list in the authors column, every value, for every, the value is a list. So therefore, for every author in the list and every other author in the list, X greater than Y is just to make sure that we don't have duplicates, like we don't have A comma B and then B comma A. So this is a string comparison. Make sure that by alphabetical order, it is there. And you add the pair of those people. And at the end of it, you find that there's actually a surprising amount of collaboration in this field. Research is a collaborative effort, massively collaborative effort. Very rarely people, relatively rarely, people write papers completely alone, right? So generally people collaborate and write. For example, you guys have formed a team and you're collaborating and writing. So you form all those pairs, and then now comes the graph part of it. Graph is very easy to get started with Network X. What do? You create an empty graph, and to this empty graph, you add all these pairs. You say, these are the edges. So here, I'd like to explain what I mean. Let me go to the drawing board. I'm now going to the drawing board. Oh, why did I not get to the drawing board? Yes, I did. So OneNote is here. Okay. So and now where did I keep my digital pen? Absent-minded that I am. Give me a moment, guys. I managed to lose my digital pen here. Where did I keep it? Yeah, here we go. So, see, guys, suppose we have a pairs of people, let's say A comma B, right? These two have collaborated. Then we have C comma D. Then we have B comma C, right? And let's say A comma D. Let me take this example.
Asif, are
We
you
can't see
sharing
the
your
screen.
Oh my goodness, I am not indeed. I am not. So that needs another little switch back and forth. Give me a moment, guys. And where's Zoom? Zoom is where? Zoom meeting. I apologize. Thanks for pointing this out. And which one do we want to share? Any better, guys? Are we seeing my screen?
Yes.
Yes. Yes.
So let the researchers be. So suppose you find these collaborations present. You made this list of pairs. Now, what can you do? You can start with A, or any researcher as a node. You can say B, you can say, let's say C, and you can say D. Now, A and B have collaborated, so you can make a link from A to B. C and D have collaborated, so you can make a link from C and D, right? And these are unidirectional links, right? So if one has collaborated with the other has also collaborated with one. So these are undirected links. Then C and D have collaborated. Now B and C have collaborated, and A and D have collaborated. Oh goodness, this makes a perfect rectangle. Let me make it something else. A and C have collaborated, let's say. Right? A and C have collaborated. Right? And maybe C and E have collaborated. So do you notice that you have a collaboration network? Right? So if A wants to collaborate with E, all he needs is a reference from C, for example, isn't it? And one more thing you notice that C seems to have collaborated with everybody else. So what happens is when you get a network, well, obviously this is a very trivial network, but generally when you get a network, you start seeing some very interesting patterns in the network. The study of complex networks and the structure, not just like drawing a huge network out and wondering what's there, but they are mathematical tools, they are abstractions. You look for patterns and structure and clustering and the degree distributions and so on and so forth. So that is there in my other book, the book that I posted online, the network book, which is still in the works, that chapter. So yeah, it is there. And of course, you should read the Network X documentation. So read the Network X documentation. Network X documentation. Also, Barabasi's book, The Network Science, by the great researcher Barabasi, is completely online, in a beautiful format. The book is also available in print. Not needless to say, the print is one of the most beautifully printed books. It's an amazing book. If you guys get a chance, or if you can, especially if your employer is part of your employment, you have a budget for books, you should certainly buy it. It's not expensive. I believe it's under $100, $50, $60 or something like that, or $70. So anyway, so we can draw the graph. Now the question is, can we draw this graph and see structures in it? So I will go back now to sharing the previous screen and the code. Where am I? Okay, so I'll share the screen now. There we go. So here you notice that how did I create this network? I created an empty graph and I added all the edges from where? From this pair that I created of edges, isn't it? Then when I print information about this network, it tells me something. There are 57,000 authors. Amongst them, there are 178,000 edges. Interestingly, the average degree of a node is 6. What do you think the average degree means?
Of collaborations each author has?
Yes, how many collaborators on average does an author have? Right. How many authors? I mean, they may not all collaborate on the same paper, but typically an author has collaborated with about 6 other authors, 6 other researchers in general, 6 to 7. And now I started it to draw this.
Asif, I
Yeah.
have one question here. So if its average degree is like the number of collaborations, so shouldn't it be a whole number, or?
No, it's a decimal because, you know, it's a fact. It is fractioned over the whole. It's just a number. No? Imagine that suppose you come up with each one author has 3 collaborators.
Mm-hmm.
Author has 4 collaborators.
Mm-hmm.
So, and suppose these are the only 2. I mean, suppose we're taking the average of these 2. You'll end up with 3.5 collaborators
Okay.
in that format.
Yeah.
Yeah. So, well, that is that. Now, I wish this nx.draw had finished by the time I was showing you guys. I'll post this code. Hopefully you run it, go to sleep, wake up in the morning, the graph will be drawn. Generally, these graphs of Network X is a bit slow in drawing graphs, very, very slow actually. For what it is worth, it takes a long time. It didn't finish, and it should finish God knows when. It was queued at 12:01. It's already 50 minutes and it hasn't finished. At some point it will finish. So in other words, Network X is very easy to learn. It doesn't scale very much to large networks. So one easy thing you can do instead of just sleeping over it is instead of taking the entire graph, you can take the graph of the 1,000 most or maybe 100 most prolific writers. So you can say, I will take only 100 writers and I will look at their graphs, the collaboration network amongst them. So that will be easy to draw. So you can take that as a challenge. How would you draw the collaboration? So let me write it down, right? How can you collaborations between the 100 most population researchers. So this would be something worth. Actually, this sentence is too long. Let us just collaboration between. This is better. Let us take a subset of the data from the collaboration graph of it. Okay. I'll leave this as an exercise for you. You can do that. Instead of drawing this big graph, you can draw that out. Now, what else can we do? This is just a starter code, guys. You can get the citation of each paper. Each paper cites some other papers, and it is cited or referred to by some paper. So you can create citation networks. Do you see that, guys? A cites B. So those could be directed edges, right? You could create that network and see, then you will find that who are the authors or which are the research papers which are seminal in the field, which have extremely high degree of citations associated with them. Right? You can find influence. You can do a page rank of the graph. See, page rank algorithm is nothing but a graph algorithm. You realize that it is a graph of web pages referring to each other. And I invite you to look up the page rank and apply it to this graph and see what comes out. Are we together, guys? Yeah. To find the most influential authors or research papers and so forth. So that is your project. This is a project that I'm hoping that you guys will do. So do you guys feel that this is a good starter, good enough starter?
Yes.
Yes.
Asif, can we go line 19?
Line 19, 14, 15, 16, 17, 18, 19. There we go.
So, here collaboration is equal. Hey, can you explain this code? Or you're calling the,
Oh, I'm calling the constructor of the graph.
okay. And
That-
that is the, and that's in the NX library, right?
That is right. That's a network.
Okay, yeah, sorry, that's new to me. So,
I have also one question like on this line 18.
Mhm.
Yeah, so I didn't quite follow that logic. So for X in author list and for Y in author list, if X grid.
Let me draw and explain it to you. One second.
yeah, thank you.
Sure. Let me now go back to sharing this. I wish this Cintiq writing pad worked on Linux. Somebody knows how to make it work. I have never been able to do it for some strange reason. Hang on. Where is Zoom? Yes, oops, not this one. Where is Zoom? Oh, there it is. So share. And are you guys able to see my writing pad now?
Yes.
Yes.
See, here's the thing. There's an archive data. Archive. So we created a data frame, right? Pandas data frame. Let me start with scratch. In this code, we have created data frame called archive, isn't it? Archive data frame contains, amongst other things, a column called, so there's a ID column, there is a title column, and there are other columns, and then it has authors column, isn't it? Now, authors column for any given entry, let's say to, or something like that, it will contain a list of, let us say A, B, right? A, B, let me take this. So it turns out authors A, B, C, D may have collaborated, or C may have. Actually, because it can confuse with the diagram above, I don't want to. Let me use some other language here. PQRST, PQRS. So let us say this paper was written by 5 authors. These are all strings. I'm not putting quotes in there. Maybe I should. This is the value sitting here in the authors column, right? And there are more columns. We won't care about that. In this column, it is it. Now, what do you want to do? You want to do this for this entire data frame. So how would you take the entire data frame? Archive, ARXIV, dot authors. If you do this, what do you get? You get this column. You get this column. This is
Yes.
so far so good, guys. Right. What is it? It is essentially a series, basically an array. Has an array, right? Array of, and each of these is itself a list, isn't it? A list of authors. So array means each of the row is an array of rows. Let me just call it author rows. Rows. It is basically that. Now, what do you want to do? You want to take for each row, that is for each of these. So you would say for author list in this. This part is now easy to understand. In other words, you want to take each of these things, items, and break it up into pairs, right? You want to make pairs. What do you want to do out of this? A PQ, QR, PR, ST, PT. You want to create all of these pairs. Am I making sense? So how would you do that? You would say for every element for X in this author list, so you take X and you take Y, some other element, Y in also the same list. What do you want to do? You want to make a tuple. You want to make a tuple, XY, right? So that you will get PQ and so on and so forth. Are we together, guys?
Yes.
Yeah, so X and Y in the list, but except that you don't want to make a pair of an element with itself, right? You don't want to create a PP, isn't it? And if you have created PQ, you don't want to create QP, right? So you want to avoid this and avoid this.
Unique.
Isn't it? So one easy way to do that is if you put a condition, if a P is greater than, X is greater than Y. What happens is X and Y are strings, right? Because X and Y are strings, isn't it? These are P, Q, R, S, T, right? These strings. These are author names. So when will X be greater than Y? It will have to fulfill both these conditions. A P, it is not itself. And secondly, in terms of alphabetical order, right? So for example, Peter will come after Adam, is greater than Adam. Why? Because A, B, C, D, the alphabetic order for strings. This is one of the tricks in programming. Both Java and Python support that you can compare strings. When you compare strings, the one that comes later, whose first letter comes later in the dictionary, is greater than the previous one. So you get the connection, guys, isn't it?
Yes.
Yes.
So if X is greater than Y, then what do? Suppose you have the pairs is equal to, let us say, a list of maybe set of pairs. What did I do? I don't remember if it was a set. I think it was a set of pairs, right? So then you would say pairs dot add. What do you want to add? The XY. So do you realize how these three for loops came through and this if condition came through now?
Yes. Yes. Thank you so much for explaining. Yes.
So all of these things, first think it through in your head. And after that, when you write code, you will realize that if you have thought it through carefully, the code will be very, very simple. Now when you go back and look at the code, it is actually pretty neat and simple. You could do it in a more complicated way. Actually, there are more elegant ways of doing it. I did not do it necessarily in the most elegant way. There are other ways also, but it is certainly, hopefully, one of the simpler ways of doing it.
As if this is basically an upper triangular matrix with off diagonal elements.
Absolutely, Shankar, you got it. Right. And so after that, I have all the pairs. What are those pairs? Those are the edges in my graph. Authors are the nodes and the pairs, the collaborations are the edges. Therefore, I can draw a graph, which is what I'm doing in the next line. And that is it, guys. So I hope this was useful. I'm going to post this to our Slack channel. In fact, let me not say I will, but let me do it right now. Otherwise, I'll forget it.
I have one more question. If you have...
Go ahead. Start your code. Give me a moment.
Sure.
Otherwise, I'll forget it. And the thing is that once I get out of this meeting, being forgetful, there is no guarantee that I will entirely forget it. Workshop kernels, networks, notebooks. Where am I? This is the archive network. Why am I not seeing it here? Oh yeah, it's the very first one, of course. It's already highlighted. There we go. And so, yes, please go ahead with your question.
Yeah, this is regarding like the original author list that you got. Like, was it a dictionary or was it a list? Sorry, I mean, I couldn't understand that.
The original data, na? See, okay, let's go through this. How the data comes. So let's review what we did. So besides this preamble and including the libraries, we just loaded it as a JSON file. When we did that, if you look at this description, there is only one field author. It's a misnomer because the author field contains actually a string of all the authors. So when I sample into it, you realize that it's a mess. Do you see how this is a messy string?
But it is not a dictionary, right? Because I see
Not-
like a name
not-
colon.
Yes. Initially, in fact, my first thought was that it is a dictionary.
Right.
I inspected it and realized that unfortunately it's not a dictionary, it's just a string,
Okay.
colon separated string. Yeah. See, I could have read it as pure JSON, but I read it as a pandas. But when you read it as pandas, it doesn't go any deeper. So maybe if I had read it as a JSON directly, I may have found it easier to get to the structure. So there are many ways in which you can address it. I addressed it this way. Then what I did is I just extracted the names. So now you notice me doing an extraction and creating a new field called authors, where the value is a list, is a proper list of names. Do you see here? List of names, isn't it? Actually, let me do one thing just to illustrate this. This is very wide. Let me just take authors.sam. Sample authors. So we can see it in all its glory. There we go. Let's try this. Oh, it can't run because this other project is running. Okay, let me go stop the other one. Oh, goodness. All right, let me kill the kernel. Restart. So I can show you. Is it restarting? Yes. So let's go from the beginning and run it. This doesn't need to be run. This is straightforward. I'll keep running it. Yeah, we'll wait here. Yeah. So where was I? Basic author. Okay. So we'll continue to run. So here we are dropping the column we don't need. Yes. So do you notice that now we have it in the right way that we want it? Look at this. Comma separated list of authors. Are you seeing that, guys? The authors field is comprised of a comma separated list.
Yes. You elaborate. That is neat.
And it is a list, not a string. It's just a list, proper data structure. So what do I need to do now is we can derive some basic statistics from it. We can do some fun stuff. We can do this. We can find the most. Typically, this will run fairly fast. 50 most published authors are here, right? Now comes the finding the collaboration networks, right? And what you can do is insert above, let's see, you could print it out, pairs. Let us see what it looks like. What does it look like, guys? It's just a tuple between two authors, right?
Yes.
So they are the edges. If you treat an author as a node, these are the edges in the node. Make sense? That is it. I will delete this node. And then comes creating this graph. Creating the graph also is reasonably fast, but drawing this graph will take a long time. So I won't go into it at this moment. Actually, the node types are not integers. I'll leave the node types as strings. So this is better. And then this on my machine will take some time to run. So guys, that's it. Get started with your project. Make some progress. I hope this is enough to get started. What I haven't done are very easy NLP things. Which tags show up most often? What are the most common tags? Right? What words show up often? Do basic NLTK. Do that. So do three kinds of analysis: tabular data analysis, network analysis, and textual analysis. Three different dimensions. And then you can build sort of all sorts of models and so forth out of it. There is ID tags, the tag terms. You can also look at the tag terms. All right, guys. So with that, I will stop today. Does anybody have a question? Otherwise, I'll stop for today. And I will also that is it, guys. So with those words, I'll finish today's session.
Thank you.
Thank you, Asif.
Thank you.
Thank you.
No, you're welcome. Bye.
Thank you, Asif.
Bye, sir.
Bye. All right, guys. Nobody seems to have any more questions that I see.
Asif, one quick question. So, are drill downs possible on the graphs?
Yes, of course. I mean, it depends upon how interactive or what you want to do with the graph.
Okay.
Yeah.
Different dimensions you can do that. Okay.
Yes. Graphs are very powerful structures. You'll see that more and more now, people are not appreciating the value of graphs. It seems to be a specialized topic, but
Right.
you'll find that everywhere the graph and graph network analysis will be there, and machine learning on graph will be there. That's why I keep emphasizing to people that get started with graphs early. Not just graphs, but graph machine learning.
Thank you, Asif.
All right. Then.
So do you recommend any books for that?
See, first learn graph. This Barabasi's book is the one I would recommend. It's freely available. It's also available in print, and a lovely book to buy in print. And then once you're done with that, on Graph neural networks, there is no book at this moment, unfortunately. It's all very researchy.
So Barabbas is tabular data.
But Barabbas is for graph data.
Anil posted the link in the channel.
Thank you.
All right, guys. All right, so now I'm finally ending it.
Thank you. Bye.
Afternoon, guys.